Good day, everyone. My name is Fang from Xuzhou University of Technology. I'm really honored to have this opportunity standing here to have my presentation for my paper. And you are welcome to communicate with me by the email shown on the screen. My paper is named Dynamic and Static Performance Analysis of Silicon Carbide MOSFETs with PWM control, and it consists of 4 parts. First of all is introduction. In this part, I will explain the reason for what I do this research and what we can do for industrial area. In the second part, I will show you the characteristics analysis of MOSFET based on silicon carbide. And in the third part, I will show you analysis of dynamic loss of silicon carbide MOSFETs. And in the last part, I give the conclusion with my modulation model and results. So let's start. Silicon carbide, as one of the third core generation semiconductor materials, has the advantages of the wide band gap, high thermal conductivity, small thermal expansion coefficients, high electron saturation drift rates, strong insulation, breakdown field, and good wear resistance compared with silicon and GaN materials. Therefore, silicon carbide can be used for manufacturing high temperature, high frequency, high power density, and radiation-resistant power electronic devices. In addition, silicon carbide materials can form oxide layer on the surface naturally, which is very beneficial to most devices. The wide bandgap semiconductor materials has the incomparable advantages of silicon materials. The power devices made by wide bandgap material can meet particular environmental requirements and meet the development needs of power electronic devices better, such as high temperature, high voltage, and high power density. The superior electrical and thermal properties of silicon carbide's power electronic devices compared with silicon devices lead to high efficiency and low volume in power converter designs. In this part, the simulation model of silicon carbide MOSFETs is built, and the dynamic and static performance is obtained. The switching loss of silicon carbide devices for AC motor control with pulse-wise modulation is calculated and analyzed. Based on the advantages of silicon carbide materials, the silicon carbide semiconductor devices have the benefits of low on resistance, high breakdown voltage, high limit operating temperature. By comparing the output characteristics and switching characteristics of silicon devices and silicon carbide devices, the advantages of silicon carbide devices are analyzed and compared. The relationship between drain DC current and gate source voltage (UGS) reflects the relationship between the input voltage and output current, also known as the transfer characteristics of MOSFETs, as shown in Figure 1. Figure 2 shows the drain current characteristics at different voltage UDS of power MOSFETs with different UGS, that is, output characteristics. And figure 3 shows the dynamic characteristics of power MOSFET. Based on the equivalent structure of silicon carbide MOSFETs mentioned above, the physical model can be comparable to the circuits in figure 4. The switching process of silicon carbide MOSFETs is modeled by MATLAB Simulink. There is already a model of MOSFET in the Simulink library, but the model is an idle model, and the characteristics of the switching process of this device cannot be observed. Therefore, the equivalent simulation model of silicon carbide MOSFET is rebuilt according to the identical circuit model as shown in figure 5. And figure 8 shows the waveforms of gate source voltage, drain source voltage, and the drain current during the turn-on process. In the initial state, the device is turned off. When the time is at 2.59 nanoseconds, the gate source voltage increases until the drain current appears. When the driving voltage is higher than the threshold voltage, at this time, the drain current increases exponentially, and the corresponding drain voltage decreases rapidly. This process is the turn-on process of a MOSFET. Influence of parasitic inductance on dynamic parameters of switching process and parasitic inductance of gate circuits are considered. For the switching loss, the increase of Lg hardly affects the switching loss. Figure 9a shows the turn-on waveforms when Lg equals 0.1 nanohertz, and figure 9b shows the turn-off waveforms when Lg is equal to 0.1 nanohertz. The overshoot voltage ratio calculated from the turn-off waveforms is about 7.2%, and for current, it's about 171% when the device is turned on. The turn-on loss is almost 51.585 μJ, and the turn-on loss is about 7.791 μJ. With the increase of switching frequency, the advantages of using silicon carbide MOSFET becomes more apparent because it has lower switching loss than silicon IGBT and MOSFETs. According to the switching resistance Rg, the switching loss of silicon in inverters is 1.55 to 4.79 times at the temperature of 25 and 3.5 to 8.6 times at the temperature is about 125, which is of silicon carbide devices. Therefore, the switching frequency of the inverter can be increased by 1.59 to 5 times for the same output power by using silicon carbide power devices. The switching phenomenon of MOSFETs is almost independent of the operation temperature. which the temperature dependence of silicon IGBTs is strong. The simulation results show that the efficiency differences between inverters can reach 5.47% when the switching frequency is about 100 kHz and the junction temperature is about 25. Significantly, the reverse recovery current of silicon diodes and training current of IGBT with the increase of temperature is down. Thank you very much for watching my presentation and don't be hesitant to contact with me by email. I'm very glad to communicate with you. Thank you. Thank you. Goodbye.